Okay, this is a problem about radioactive decay. So you've seen problems where there was exponential growth or exponential decay before. You've done these problems in previous classes, and we know what type of model that we're going to have in any exponential decay problem. So before we even read this, we know that it's going to be a PERT model. So there's some initial amount times e to the RT power. Now, why does that work? How does it work? So let's read on here. We want to write a differential equation that describes the rate of decay, which is proportional to the amount present. Okay. And then we're given an initial condition that we start with 100 grams at time 0, which is usually in years at the time. And we're also told that the half-life is 10 years. Okay, so we're told to use the letter Q. So we can start off by writing that dq over dt equals, and it's proportional to the amount present, so it's just going to be maybe r times q. So there's our differential equation. And if r is less than 1, we can expect that it's decaying. If r is greater than 1, it's actually exponential growth. All right, so we need to solve this, and we're actually going to need to figure out what that r is, and that's going to have to do with this notion of the half-life being 10 years. All right, so we separate the variables. So get all the q's on one side, so we divide by q, 1 over q dq equals r times dt. Get our variables on opposite sides. Now we're ready to integrate both sides of the equation. All right, on the left we get the natural log of q equals, and on the right we're just going to end up with r times t plus a constant. Okay, to solve for q, we need to exponentiate. So q equals e raised to the rt plus c. And as we saw in the previous problem, that plus c in the exponent really just works out to be some constant out in front. So k times e to the rt. So that looks a lot like this PERT formula that I had referred to before. And now we need to figure out what r is and what k is. We know the initial condition, which I probably should have identified first, q of 0 equals 100. It's not an initial value problem without that initial condition. All right, so when t equals 0, q equals 100. So we'll plug it in. 100 equals k times e to the r times 0. Oh, so that just implies that k equals 100, because e to the 0 is just 1. So our new and improved equation is q equals 100 e to the rt. If we can figure out what r is, we have our model. All right, we are told that the half-life is 10 years. So after 10 years, we can expect that the quantity will be 50 grams. So 50 equals 100 times e to the r times 10. And that's because we were told that q of 10 equals 50. Okay, once we can just solve for r. We divide by 100, then take the natural log. So divide by 100, you're going to get 1/2 equals e to the 10r. So then we take the natural log of both sides. The natural log of 1/2 equals 10r. So that implies that r is the natural log of 1/2 all over 10. So we know that q, or maybe even q of t if we want to use the function notation, equals 100 times e raised to the, and it was the natural log of 1/2 over 10 times t. So that gives us our final answer here.